Good afternoon, everybody. My name is Michael Higgins. Over the past few months, I have been investigating novel learning-based control techniques for aircraft as part of the J.J. Slade program. Today, I'm excited to present my progress with this work and the future of my research. Instead of jumping right into the work I've been doing, I would first like to take a step back and talk about the concepts underlying the control system add-on I've been focusing on. After proper explanation, I will touch upon the two primary aspects of this project. The first aspect is the control system add-on itself and the simulations carried out to demonstrate its viability in a simplified environment. The second aspect involves developing the hardware necessary to implement this control system add-on in real time. This project is ongoing, and as such, I will briefly touch upon the exciting future of this work towards the end of the presentation. So let's talk about drones. As many of us are aware, the drone market has grown rapidly over the past couple of years and is projected to continue growing over the next decade or so. Drones are being explored for many different commercial, military, and scientific applications, the list of which would take up an entire presentation in itself. This is primarily due to the many advantages that drones possess. Many commercial models are lightweight, possessing few moving parts, and have autonomous or semi-autonomous capabilities. That being said, drones have two main disadvantages. First, they are underactuated, making them impossible to control in an arbitrary manner. Second, they are governed by nonlinear dynamics, making control design a particularly interesting challenge. I would call it a fun challenge, personally. Speaking of control design, well, what's a control system? Control systems govern the response of a dynamic system. We all interact with control systems on a daily basis, but one of the classic examples is cruise control in a car. Many dynamic systems can be described by an equation or system of equations. When modeling systems, these equations are typically referred to as the plan. For cruise control, the equations of interest would be those governing the acceleration of your vehicle. Control systems attempt to manage the system dynamics in a desired way. In many cases, the controller attempts to drive a system towards some desired reference state. In the case of cruise control, we want the vehicle to approach and maintain a certain speed as closely as possible. Many times, this is accomplished using feedback or information about the current state of a system. Although simple, one of the primary drawbacks of this type of control is that it cannot enforce constraints on a system state. If our vehicle had this type of controller, for example, we couldn't tell the control system to limit our acceleration to below a comfortable threshold while maintaining our certain speed. This presents a problem for many applications. Thankfully, some very clever people, not myself, have thought up other ways to enforce constraints on a system. One of the more popular methods of constraint enforcement nowadays is with a reference governor. A reference governor is an add-on control scheme that typically augments a closed-loop feedback control scheme. Reference governors enforce constraints by controlling the reference that is sent to the closed-loop feedback control system. This modifies the way the system dynamics behave, thus avoiding constraint violations. One of the primary advantages of reference governors is that they can be applied to nonlinear systems with complex dynamics, such as drones. Recent advances have improved upon the reference governor. These advances include the explicit reference governor, or ERG. ERGs guarantee constraint satisfaction by manipulating the derivative of the applied reference sent to the feedback control loop. ERGs are computationally efficient, and as such, they can run on the types of low-cost hardware typically utilized for commercial drones. While extremely useful, the primary drawback of ERGs as they relate to drones is that they require thorough knowledge of the dynamics of the system to be controlled. This is not always possible for individual drones or new classes of drones. Thus, further developments are required. This brings us to the Learning-Based Explicit Reference Governor, or LERG, which has been the focus of my work. The LERG has recently been developed as an answer to the ERG's inability to function without complete knowledge of the system dynamics. The LERG, however, is still based on the computationally efficient control law governing the ERG. Essentially, the LERG utilizes an algorithm to learn how to avoid transient constraint violations over time. This learning algorithm only has knowledge about current constraint violations and limited information about previous constraint violations. Eventually, as proven by the pioneers of this control scheme, a system with an LERG augmented control system is guaranteed to avoid transient constraint violations. For my work, I've modified the original LERG algorithm to also allow for enforcement of constraints in the steady state. What you see on the slide is a simplified version of the LERG learning algorithm without all the messy mathematics. This algorithm is centered around two unique functions. The first is an epsilon function, which summarizes the available information about a system state as a single scalar value. The second is a gamma function, which stores information about previous epsilon values that were recorded when a constraint was violated. During operation, when the epsilon function of a system approaches the appropriate area of the gamma function, the feedback control system's reference value is modified to slow down the system response and avoid a transient constraint violation. This algorithm also checks to see if a constraint will be violated in the steady state and modifies the system dynamics appropriately if this is the case. This step represents the modification I made to the original algorithm. One of the neat things about this learning process is that it can be done in a simulation environment with the learned gamma function implemented on a vehicle, or it can be done without any prior learning in real time. So we have a control system to impose some constraints on a UAV, but what good is a control system if we can't actually implement it? Well, over the past few months, myself and a few other students have been working on developing, building, and testing the hardware necessary to implement the LERG control algorithm and other control systems on a drone in real time. The system that was developed for this purpose is known as the Blackbox. You can think of it as a hacked RC aircraft transmitter that allows us to record, modify, and send signals to a transmitter or from the transmitter to an aircraft in real time. The system utilizes several teensy microcontrollers to read voltages from the transmitter, which correspond to joystick positions, and send new voltages. This system interfaces with a computer to allow for implementation of a custom control algorithm through MATLAB. However, in order to implement the LERG on a drone, we still need some real-time information about the drone state so that we can determine if constraints are in fact being violated. We elected to utilize the Vicon imaging system in the Emil Buehler Aerospace Lab to gather information about the position and orientation of a commercial drone. A Vicon imaging system utilizes a series of strategically placed cameras to precisely calculate the position and orientation of an object in 3D space. This data is then fed into MATLAB to be utilized with the control algorithm of choice, in this case, the LERG. Using MATLAB, numerous simulations were conducted where a drone with an LERG augmented control system had various constraints placed on it. First, orientation constraints were applied. These may be useful when a drone is transporting sensitive cargo, such as medical supplies or COVID-19 vaccines. The drone was commanded to move to different reference locations in a two-dimensional plane without tipping more than 10 degrees in its pitch or roll axis. The reference positions were taken from a 50 meter by 50 meter square. As seen in the figure to the left, over time, constraint violations, defined by exceeding the bounds of the red lines, generally become less frequent in the roll axis. Additionally, the magnitude of these constraint violations also generally decreases with time. Eventually, the LERG algorithm learned a gamma function that always resulted in constraint satisfaction, as shown in the figure on the right. Further tuning of the LERG parameters would allow for the simulated UAV to approach the constraints more closely, which would result in a faster response to a given reference command. However, this would result in a longer learning time. Now, one may also wish to enforce a position constraint for a drone, say, to avoid restricted airspace. I restricted the drone from moving more than 40 meters away from its original position in the X and Y axis. However, this situation is a bit more complicated than the previous one with orientation constraints. This is because a given reference position may represent a constraint violation in the steady state. This is in contrast with the orientation constraint, where a drone will always end up in a steady state that does not violate the constraints, since it will always level out upon reaching its desired position. While the original LERG algorithm is not equipped to enforce steady state constraints, the modification that I made to the algorithm can impose such constraints. Since the position constraints are never violated in a transient manner, however, no learning actually occurs, as you can see on the left. On the right, you can see how the position changes with time with respect to the original and modified reference. One may also wish to impose a constraint on the control input or actuators of a system as opposed to its state. This is also possible with the LERG. For a drone, we can constrain the thrust that the motors generate. This may be useful for prolonging flight time or avoiding sudden acceleration that can damage cargo. Since thrust generation would result in transient constraint violations, the behavior of the thrust variable is similar to the behavior of the roll variable when an orientation constraint was applied. Now, imposing these constraints individually is great, but a much more realistic and useful situation would be imposing multiple constraints on a UAV at the same time. Luckily, we can do this with the LERG. The same thrust and orientation constraints were imposed along with a nonlinear three-dimensional position constraint. This new nonlinear position constraint essentially forces the drone to stay within 16 meters of its original position, which, geometrically speaking, is a spherical region. Here you can see the roll and thrust over time after learning. As with the orientation constraints, further tuning of the LERG parameters would result in a faster response to a given reference command at the expense of a longer learning time. And here you can see the position constraint imposed successfully. Thus, all the constraints were successfully imposed concurrently, validating the application of the LERG for the constrained control of a UAV in a simplified simulation environment. So that covers the software side of things, but what about the hardware? Up to this point in time, we've been able to track the trajectory of a drone in real time using the Vicon imaging system. We've also been able to apply a closed-loop PID controller to modify the altitude of a drone in real time. Thus, the Blackbox is successfully able to read and modify transmitter signals in real time, allowing for the implementation of the LERG on an actual drone. So, to briefly summarize, over the course of the past several months, I've been able to successfully implement an LERG augmented control system on a simulated UAV with numerous constraints. These constraints included orientation, position, and thrust constraints, which were imposed individually and concurrently. After some time, the LERG successfully learned to avoid transient constraint violations. Modifications to the original LERG algorithm also successfully prevented steady-state constraint violations related to position in both 2D and 3D space for linear and nonlinear constraints. Finally, a system known as the Blackbox was designed, built, and tested in a limited capacity to allow for the implementation of an LERG on a drone. Testing showed that the Blackbox will, in fact, suffice for this purpose. Unfortunately, due to university restrictions on laboratory access for undergraduates, I've not been able to take my work any further up to this point. However, I will fortunately be able to do so in the coming weeks. The first objective is to implement the LERG augmented control scheme on a UAV in real time using the Blackbox. This will be accomplished using a simulation-derived gamma function on a vehicle with well-understood dynamics, specifically a standard quadcopter. After this, the LERG will be implemented on a UAV and directed to learn a gamma function in real time. This will be accomplished using conservative learning parameters. Finally, a similar implementation of the LERG will be utilized to control a completely novel type of vehicle whose dynamics are not well understood. Eventually, this work could potentially be extended to aerospace vehicles other than small UAVs. Now, before I finish, there are a few people I would like to recognize for their role in this project. First, I would like to thank Dr. Laurent Berlion for his support of and assistance with this research, Joe Petrocelli for his work in manufacturing the Blackbox, and Juan Francisco Lopez Miro and Mike Vogel for their work testing the Blackbox. I would also like to thank Dean John Patrick Antoine for coordinating the James J. Slade program and the Rutgers School of Engineering for their continued support of this program. I would like to also thank Gaurav Agarwal and everybody else that helped to make the program run as smoothly as it did this year. And lastly, thank you all for listening to my presentation. I would be happy to answer any questions you may have during the poster session. On that note, I hope you all enjoy the rest of the symposium.